All right, so we're trying to discuss the idea of continuity again today. Continuity is something we talked about probably the very first day of class. If you go back to page 1-1 of our course pack, and the first 3 pages are all vocabulary terms, and it took us about 2.5 days to get through all those terms at the beginning of January. And I believe this is on page 1-1, continuous function, a function whose output varies continuously with the input so that there's not a jump from one value to another. All right. So this is not what we would consider a very good mathematical definition. In fact, it's not a good definition, period, because we're defining the word continuous by using the word continuous. That is a really bad, it's a redundancy that doesn't really help you understand a definition. We need to define things in terms outside of the word itself. And so this is why all the way back in Unit 1, we had to go with more of an intuitive definition. We had to say it's a graph that we can draw with one continuous motion without lifting the pencil. So if I had a graph here and I came through and I never had to take the pen, pencil, whatever off of the paper, there's continuity. It doesn't have any breaks in it, right? If I was coming along and something happened and I had to like pick it up somewhere else, now we know that it has a discontinuity, and we talked about the different kinds of discontinuities there were back on that same first day of class, and we will review those today. So not a great definition, and definitely not a mathematical definition. A lot of things working against it. I mean, we understand it. It's a good intuitive definition. We understand that you can't lift the pencil, even if it's just a hole, right? Even if it's a removable discontinuity, and you only have to lift that pencil, right? Just for a second. Well, still a discontinuity. You still had to lift the pencil. So we're gonna talk about how we can use limits to get a much stronger idea mathematically of what continuity really means. And yeah, we're going to review the different types of discontinuities as well. That is the goal of the day. So, example 1, we're on page of 314 of your notes, or it might be page pi, in honor of the ratio of a circle's circumference to its diameter. But regardless, this is example 1. Gives us this nice pretty picture. Looks like a piecewise function that's defined between 0 and 4, and it asks us to find the points at which the graph of the function is continuous and the points at which f is discontinuous. Now, I'll tell you right off the bat that you're not going to be able to find all the points where it's continuous, or at least list them, because there are infinitely many of them. In fact, even if we just said, let's just find all the points where it's continuous from here to here, right? Because of the density of real numbers, it's infinitely continuous just in that little tiny region. And so what we're best doing on problems like this, what your strategy should be, is let's start with the second part of what it's asking. Where is it discontinuous? And then we can just turn around and say it's continuous everywhere else. All right. So I think that with that strategy in mind, that you would be able to do this pretty well if you understood continuity in Unit 1. You'd say, well, it looks like it's continuous, or everywhere up to 1, and then there's a jump discontinuity, and then it's continuous up to 2, and then there's a removable discontinuity or a pointwise discontinuity, and then it's continuous until we get to the end of 4. All right. I know the axes aren't labeled, but it told us here that, you know, the interval is from 0 to 4. I guess here's what it told us. So there you go. No problem. You know, we said that it's discontinuous at x equals 1 and at x equals 2. So that means it's continuous everywhere between and including, because they have closed dots at the ends of this interval. It's continuous everywhere greater or equal to 0, less than or equal to 4, except x equals 1, x equals 4. And that's pretty much what, you know, they ended up saying. It's discontinuous at x equals 1, it's discontinuous at x equals 2, and then it's continuous everywhere between that. But that doesn't really expand on the idea of continuity. So we're going to come back and finish this up in a second where we look at this aspect of it right here. But first, we're going to actually define continuity. So 2 weeks ago, we learned what a limit was. Huge step for you, moving past algebra and into the higher level toward calculus. Last week was a big week, because even though we've done a ton of end behavior previously, you know, we actually put it together and understood how we could actually prove mathematically what end behavior models are, and understand horizontal asymptotes and vertical asymptotes at a higher level. Well, this week is another big week, because we're going to understand really what continuity is all about. So here is the definition of continuity, also on page 314 or page pi of your notes. Continuity at a point. So it breaks it into interior and exterior endpoints, not exterior, but if it's an interval, then you have to worry about the endpoints, which would just be a one-sided argument because you're only approaching it from the right or from the left. Mostly this is what continuity is all about, interior points, okay? So a function, y equals f of x, is continuous at an interior point c. So c is just some x value, right? That is apparently, the way that we have it set here, between a and b, okay? If the limit of f of x as x approaches c is equal to the function's value of c for all values c. Now, this is a big idea. This is a tremendously large idea. So we're going to break this down, and I'm going to repeat it a million times over the next like 4 or 5 slides, and you're probably going to get irritated with me, which, you know, I'm sorry if you do, but this is a simple statement, and it's just this is equal to that, but it tells us a ton. And we've got to understand a couple things. We've got to understand what functions do, and we've got to understand what limits, when limits exist, what limits are, for us to really put these pieces together, okay? So let us give this a shot. Let's start with the 2 things that have to happen. Okay, I'm going to break this definition into 2 major components. The first component is for any c in the domain, okay, of our function f, for any c in its domain, or at least its interval, right, if it's only defined on an interval, okay, the limit exists. That's what this is saying right here. It's not saying that the limit of f of x as x approaches c is equal to f of c, which is what we eventually want to work to. It's just saying that there is a limit. Now, what does that mean? What does it mean to say a limit exists? Well, what we learned 2 weeks ago is that a limit, notice this isn't like c from the left or c from the right. It's not a one-sided limit. This is a limit. A 2-sided limit only exists if coming in from the left and coming in from the right, we are approaching the same location. So we have to be approaching the same height, the same line up. That has to happen. So that rules out 2 major discontinuities right away, which, like I said, we're going to review those in a second. But if I have a jump discontinuity, I'm not approaching the same height, that's out, right? And if I have an infinite discontinuity, and so I have like a vertical asymptote, that's not gonna, the limit won't exist there either. So we can't have continuity of those. Cool, okay? But if you remember, one really interesting thing from a couple weeks ago is that we found out when we have removable discontinuities, when I have holes, the limit still exists. Because even though there's not a point at the arrival location, right, the two sides of the function are still approaching the same spot. You know, you and a friend who live on opposite sides of town are going to meet at a restaurant, and you're driving down the road toward this restaurant. It doesn't matter whether when you get there the restaurant is there and you go in and have dinner, or when you get there there's been a fire and there's just a pit left and the restaurant is gone, and you still arrived at the same spot. And that's basically what we're talking about. The limit exists. So that's a big deal. But here's where we up it a notch right here. For any of those C's, for any of those C values, okay, the limit L that we just said exists is equal to f of C. What does that mean? It means it's equal to the function's actual y value at that point, which means I don't have a, well, first of all, it means it's defined, so it's not just a hole with nothing there. There's a point somewhere, right, where we have a y value for that C value. But more importantly, that y value is exactly the same point that your graph was approaching. The y value is equal to the limit, is what we're saying. There's no holes, okay? So step one takes out your infinite discontinuities, takes out your jump discontinuities. Number two takes out the one kind of continuity that allowed a limit to exist, which was your holes. And if there's no holes and there's no other major discontinuities, right? So there's no removables and there's no non-removable discontinuities. That means that there's only one thing that can happen, and that is that your function is continuous. And so we take these two pieces, and since they're both equal to L, we put them we put them equal to each other. That is the definition. And this may look way different than what's in your notes, okay, or the page we had, you know, before this, but it's just breaking that definition into the two major components, okay? The first part is saying that our graph is moving toward the same spot. And this is saying that when we get to that spot, there's a point there, okay? This is saying that we're both heading to the same restaurant. We're driving toward the same restaurant, okay? And so we're going, even though we're coming from different directions, we're going to arrive at that same parking lot. This is saying that the diner is not burned down. The restaurant is not burned down. We're going to be able to go inside and have dinner, okay? I'm not actually going to go to dinner with any of you. Not that we wouldn't have wonderful conversations, but it's just an example. So I don't want you to get, you know, like, oh, ooh, we're going to go to dinner. We're going to talk about math. No, just let's clear that up. So here we have two different sides of the function coming together, but there could be a hole there. There could be a hole there, right? There could be a hole at C, but we know that the limit exists because I'm moving towards the same spot, right? But now f of C is equal to that limit. And so that means that we have continuity. The only difference with the endpoints at the end of an interval is we would only be talking about, in this case, the right limit. We'd only say that the right limit of f of x is equal to f of c. And in this case, we're only coming from the left. So you just talk about one-sided limits if you're talking about the ends of your interval. That is the only difference between the interior definition, which is our primary definition, and then the endpoint definitions, which is just a small little addendum to that to make sure we cover all the cases. So very important. It's so important, I'm not going to give up. Okay, here we go again. Here we go. Limit of f of x as x approaches c. So my function's coming in towards c here. We're getting closer and closer to f of c. The limit exists. But when I get there, f of c is the same height as the height that my function was approaching. That means it's impossible for there to be a hole, no removable discontinuities, we're good to go. So same idea, Okay, just slightly different picture. Here we go, one more time. I know you're getting tired of it, but this is so important. Limit of f of x as x approaches c. What does this tell us? It tells us that the limit exists, which means both ends of the graph are approaching the same location, or better yet, the same height, right? We're moving toward the same height. But guess what? F of c, okay, tells us when it's equal to that limit, that when I get there, okay, I have a bridge that connects the two pieces. Okay, I can't have a hole. And so here's the idea. The limit tells me that I'm moving towards the same height. The big question is there anything that's going to be there when I get there? If there is a hole, I don't have continuity, do I? That would tell me the limit was not equal to f of c. But if the limit is equal to f of c, like the definition states, ta-da, we go right through that point, we are bridged. That is the definition of continuity. So if you're still struggling with the concept of limits, we're now 2 weeks in, you've got to reach out to me and help you with that concept, because it's very conceptual, and it's really important you understand what it means for a limit to exist versus not exist. Limits exist at all continuity points, right? But not at all discontinuity points. Sometimes they exist, sometimes they don't, and that's where we spend a lot of time talking about the different types of discontinuities, and we're going to review that again today, right? So going back to example 1 now, we can really break this down. So here's the part about, let's blow this up a little bit. Here's the part about the endpoints. And so you can see that the limit exists at one endpoint, which is at 0 over here, okay, because Si, now I'm getting really lost. Let's grab this and do this. Fantastic. All right, so as I approach the endpoint at 0, I'm only coming in there from the left, right? And so that's the only difference with the definition. And then as I come into the left limit toward the right endpoint, right, the right endpoint of the interval, I'm only coming from the left. So that would be, coming into 4 over here, and I'm only worried about a one-sided limit on those cases. So that's just a quick, discussion of what happens at the endpoints. Usually, that's not what we're concerned with. Almost always, we're concerned with what's happening inside. So this is the statement right here that makes or breaks the whole thing. At any point between 0 and 4, except at those two discontinuities we found at 1 and 2. Don't know why there's an extra comma there. That's kind of weird. This is what happens. The limit of the function is equal to the c value. So, for example, let's take 3, right? As I come into 3 from the left side, from the right side, I'm approaching the same height. I'm approaching a height of 2. And guess what? The function's height at x equals 3, okay, is 2. So it bridges the limit. It bridges the two sides of the road coming together. That's what it's all about right there. All right. I told you you would get tired of me repeating this, but I only do it because it is so important. All right, so let's move on. I think you guys are probably ready to leave this definition. It's there on page pi. And go back and just keep checking it out until you really feel good that this is something you understand quite well. And if you don't, you just got to reach out to me, and I will put in some different ways or find some resources for you to help you understand that. This is the second example. I will not spend as much time on this, but find the points of continuity and the points of discontinuity for the greatest integer function. Well, when we defined it back in the day, we know that at every single integer, it jumps to the next integer. So at every single integer, right, there is a jump discontinuity. So if we specifically look at this case right here, which has the limit, right limit and left limit as we approach 3. Okay, we can see, I'm just going to blow up that part of the graph. So where's 3? Here's 3. So we're approaching 3, right? As I come in from the left side, I'm at a height of 2. That's right here. But as I come in from the right side, I'm at a height of 3. And so because there is a jump discontinuity, the limit doesn't even exist there, and we're done. There cannot be continuity. There's really 2 checks if you want to know whether continuity exists at a point. There's really only 2 things, and it aligns exactly with the 2 parts of the discussion, the 2 parts of the definition that I broke down for you back here. So I'm gonna go back here just one more quick time. Okay, first you got to check that the limit exists, because we just found at 3 there the limit didn't exist, so you're done. You don't even have to do the second part. We checked the first part. This is not a continuous function. The second part, right, is once you know that limit does exist, you got to make sure there's not a hole there. So then you have to find the function's value at that point, and if it equals the limit, then you have continuity. So you just do those 2 checks. And this example showed us that at any integer value, the limit does not exist, so we're done. Now, on the other hand, at any interior point to an integer value, the limit will always exist, because you just have this horizontal line. Both sides are approaching a point that's there. Your limit exists. So there you go. Moving on again. We get to, now, so we're on page 315 now, which apparently also has its own special symbol, right? I'll let you, literary and historical buff, decipher that one. But this is the catalog of discontinuities that we found back in Unit 1. I mean, it was like the first or second day of class. We really broke these down and had a good, looked at some different examples of these, etc. So this is just a nice little resource, so you don't have to keep going all the way back to Unit 1 to dig this information up in case you've forgotten some of this stuff. So let's go ahead and go through some of these pieces. So we're just going to start off with a continuity itself, right? Just to make sure we understand the difference between discontinuities. And here we see the 2 sides of the graph, approaching the same spot, and the point's actually there. So we know what continuous functions are. We really know what they are now. We had an idea of what they were previously, but now we feel much better about that. So here's your removable discontinuity. Removable discontinuities, or you can call them pointwise discontinuities. Some textbooks use the word pointwise because they occur at a single point, are created by holes. Now, please don't, some people call them holes, like what kind of discontinuity is that? That's a hole. The problem with that is that a hole is not by definition a type of discontinuity. It causes a removable discontinuity. Okay, so I know that's a little bit semantical there, but a removable discontinuity is caused by a hole, but a hole is not the discontinuity itself. So a hole is a type of thing that happens with the function, or a type of thing that is created by a function. Graphically, we get what we call the removable discontinuity. So I know it's, like I said, a little semantical, but it's a common mistake, so I'm just trying to point that out so you avoid it. Now, here is another removable discontinuity. The only difference is this one, the function is undefined at x equals 0. At x equals 0, look, not only is there a hole at 1 where there's supposed to be a point, but there are no points anywhere else. On the next picture, they actually have it defined. So the limit, what we would say is, let me go ahead and jot this down for you, just because we're so good with limit notation and all that kind of stuff now, right? The limit of f of x as x approaches 0 is equal to 1. The height from both sides is definitely a height of 1. However, f of 0 itself, right? F of 0, well, look at that. It's up here. It's 2. And so do you see how these two things right here are not equal to each other? Well, that is the definition of continuity. Those two things have to be equal to each other. But we know that one's not equal to two. So that's definitely not a continuity. So the limit does exist, but the continuity does not exist. Okay? Removable discontinuity. Here's a jump discontinuity, which we most typically find in piecewise functions. Although we do have one of the parent functions that has jump discontinuities, infinitely many of them. In fact, we can't call them jump discontinuities, I think, because they're a function. Well, I guess you can. I mean, they are jump discontinuities. I think we can't call it a piecewise function because piecewise function has to have a finite number of pieces, and the greatest integer function has an infinite number of steps. So the function can't be called a piecewise function, but it definitely does have infinitely many jump discontinuities. And that's where, you know, we still have, you know, one-sided limits that exist. As we come in from the right, the limit is 1, and as we come in from the left, the limit is 0, but the limit doesn't exist, so continuity cannot exist. Same thing with infinite discontinuities. This is 1 over x squared. We're more used to 1 over x, which just has, you know, one guy down here, one guy up here, so that one of the branches is approaching positive infinity and the other negative. But even if they're both approaching positive infinity, like 1 over x squared, infinity is not a real number. So we could describe the one-sided limits, right? We could say that the limit of f(x) as x approaches 0, say from the left, right, is equal to infinity. Although it's not really equal to infinity, that's more describing a direction. Okay, so we're allowed to write that, but infinity is not a real number. So once again, the limit does not exist at 0, so we cannot have discontinuity. Remember, if part 1 of our continuity definition fails, we're done. We don't have to check the function's value. In this case, we couldn't because it's undefined. The oscillating discontinuity is the one that you just aren't going to see. It definitely occurs. We talked about it back in Unit 1. It might have popped up on a multiple choice question, like which one of the following is not a type of discontinuity, and you had to know oscillating was a type of discontinuity, but it's not one that we can really analyze, and so you're just, at least at this level, you know, in calculus, you probably do a little bit more with this type of thing. The whole idea here is that because the numbers, when we start putting really small numbers close to 0 into the 1 over x, those fractions get huge, which makes the sign oscillate faster and faster. And so basically, sign is oscillating infinitely fast as we approach 0, which causes which causes chaos in the function. It causes it to basically rip. And so there's discontinuity at 0. And even close to 0, things get really nasty. But that is the oscillating. And I think that was it. Well, there was one. I got to be honest. I did not include this one in Unit 1 because, you know, you were new to the class. I just didn't want to freak you out because it is kind of a scary one that does cause some people some discomfort. It's called the dactylian discontinuity, and it's kind of rare. I don't think you're going to have to worry about it much, but you know, you might if it happens. I don't know what was. Did you hear that? Uh-oh. Uh-oh. Oh yeah, I knew it. Oh, here it comes. There it goes. And there it was. I shouldn't have even brought it up because I knew it was going to happen. So that's where pterodactyl just rips off a big chunk of your graph and you never see it again. And once again, there's not much we can do with that. So don't worry about that one. All right, moving on. This is simple and yet often misunderstood. So just make sure you understand this discussion, and I think you'll be fine, because this is actually a big chunk of tonight's homework is about this definition right here. For a function to be continuous on an interval, okay, it has to be continuous at every single point in the interval. There can't be any breaks at all. All right. So if our interval is all real numbers, from negative infinity to infinity, we would say that it has to be continuous over all real numbers. That is continuity on an interval. Now, what makes a continuous function? The definition of a continuous function is it's continuous at every point of its domain. So that's the key difference here. When you're talking about continuity on an interval, you have to include every single value, whereas continuity for function only talks about the domain. And we know some functions don't have domains of all real numbers, right? So if I look at example 3 and I just ask somebody what it says, this is the function 1 over x. Is it is it a continuous function basically? Well, we know very well that at x equals 0, there is a vertical asymptote. A vertical asymptote is not a type of discontinuity, but it causes an infinite discontinuity. Now remember, it's caused that because that vertical asymptote, your graph, is going to attempt to go either towards positive or negative infinity, depending on which side it's coming from, right? So at x equals 0, there is an infinite discontinuity that's caused by a vertical asymptote. Similarly, don't call the type of discontinuity a vertical asymptote. The vertical asymptote causes the infinite discontinuity. It's not a discontinuity on its own. And there's the dog. Hold on. All right, I think she is feeling better about the trash truck being gone now. So is it a continuous function? See, most people would say no. This is not a continuous function. There's an infinite discontinuity at x equals 0. What we could say is it is a continuous function because the domain of this function, if you recall, doesn't include 0. It's all real numbers except for 0. And so you don't have to worry about 0 when you're describing the continuity as a function. Now, we couldn't say that it was continuous over all real numbers. It is not continuous over all real numbers because there definitely is an infinite discontinuity at x equals 0. But as far as the question goes, it is continuous over its entire domain. So it is considered a continuous function. I think your first 10 questions are problems like this. And you're going to be looking at functions, and what you need to recall is what's my function's domain. If you need to go back to Unit 1 and review a little bit of that, that's fine. That's why we kept pages like 10 through 13 with those little capsules of all the information all together, so it's really easy to look up. But if the only discontinuities occur at places that are not part of the function's domain, then you absolutely can say that the function is continuous. By definition, it is, right? It just has to be continuous at every point in its domain. All right. Other continuous functions. So all polynomial functions are continuous everywhere because they're defined everywhere, they're continuous everywhere, they're smooth, they're beautiful. They're calculus's favorite functions. They should be yours too. Rational functions are continuous everywhere except where their domains are equal to 0, right? Or their denominators are equal to 0, sorry. And we learned that by doing dozens of these problems back in Unit 1, and then we did a lot of them the last couple weeks when we were exploring limits. When there are zeros in the denominator of a rational function, we're either going to get infinite discontinuities caused by vertical asymptotes or removable discontinuities caused by holes. But those functions, those points will never be part of their domains. So rational functions will always be considered continuous functions. Other functions that are always continuous, absolute value functions, never break at all. We just have like a V vertex and that's it. Exponential functions, defined everywhere, never have breaks. Logarithmic functions are not defined everywhere, right? They're only defined on one side or the other side of their vertical asymptote. But throughout their domain, whatever that domain will be, they never break. Trigonometric functions, well, sine and cosine specifically have domains of all real numbers and never have any breaks. The other four functions have infinitely many vertical asymptotes. We remember that, secant, cosecant, tangent, cotangent. but none of those values are part of the domains. So they are continuous functions by definition. Radical functions. If they're odd roots, they're continuous everywhere. If they're even roots, then they're only going to be defined on one side or the other, right, of their start point. But they're not going to have any breaks within that part of the domain. So absolutely. All those functions are continuous at every point of their domains, okay, by our definition. And so polynomials, rational functions, absolute values, exponentials, logarithmics, trigonometric functions, and radical functions, all continuous functions by definition. That's most of our parent functions right now. Are they continuous over all real numbers? Totally different question, right? This is more of an interval question. Are they continuous over the interval of all real numbers? Well, polynomial functions, yes. Rational functions, no. Anywhere they have zeros in the denominator, see you later, right? Absolute value functions, yes. Those V's never have breaks in them, do they? Exponential functions, yes. Logarithmic functions, no. They're not even defined over all real numbers, right? They're going to be defined on one side or the other. Same thing with radical functions. Now, if it's an odd root, yes. But if it's an even root, no. Trigonometric functions, sine and cosine, yes. Sine and cosine, yes. But the other four would not be defined continuous over all real numbers, okay? So that's just a little review. But going back to Unit 1, this is, I think, page 8 or 9 from our course book. And then like pages 10, 11, 12, 13 is where we actually wrote down all the meaty information on all these functions. We can go do that. But, you know, if we broke it down super fast here, you know, these are all polynomials. So they're going to be continuous everywhere, right? They're continuous functions and continuous over all real numbers. Let's put infinity. That doesn't really make sense, does it? Should have probably put an R there for real numbers. But rational functions are continuous functions, but are not continuous over all real numbers. Root functions, well, if it's even, well, they're all continuous functions. If it's an even root, it's not continuous over all real numbers. If it's an odd root, it's continuous over all real numbers. Exponentials, yes, continuous over all real numbers and continuous function. Logarithmic functions, continuous functions, yes, but not continuous over all real numbers. Only one of the parent functions is not a continuous function. I don't know if you guys have figured it out yet, but we've already played around with it today. The trig functions, these two are both continuous functions and continuous over all real numbers. The other four, though, although they are continuous functions, not continuous over all real numbers. Absolute value function, yes. Continuous function, continuous over all real numbers. Greatest integer function. See, this is the one, not continuous. It has a domain of all real numbers. The domain is all real numbers. But every time there's an integer, we have a jump discontinuity, don't we? So that's the odd man out. Logistic function is continuous and continuous, but we don't play with that one very much, do we? All right, moving along. Properties of continuous functions are very similar to like how we had properties of limits, where we could, you know, add, subtract, divide, multiply, take compositions of limits, and the limits would, if you just did the same operation with the limits themselves, the functions would generate the same values. Well, similarly, we're not generating values here, but we're generating a property, or we're preserving a property would be a better way to say that. So if basically this says if you have two continuous functions, f and g, and you add them, subtract them, multiply them either by each other or by a constant, divide them as long as the denominator isn't zero, right? You will create new continuous functions. And even if you put one of them inside of the other, we call that composition. Remember, composition of functions. So f of g of x, if f and g are both continuous, f of g of x will also be continuous, okay? All right, here's an application of that. If h of x is sine x squared, I can break that into, let's say g is sine and f is x squared. So now g of f is equal to h. And because sine is continuous and x squared is continuous, that's proof that sine of x squared is continuous, okay? Same thing here. Absolute value function is always continuous, right? We just get those nice V's with those. Cosine, always continuous, just an oscillating graph. So what happens when I put the cosine into the absolute value, which is exactly what they're asking me to do here. So G is absolute value, F is cosine. So G of F in this case, right? G of F of X, okay, that's not gonna work, but you get the point, is gonna have to be continuous by the property we just talked about here. And in this particular case, here's a pretty little picture of what that would look like. It kind of looks like a cosine graph, except the absolute value takes all those negative ratios, and instead of perpetuating them into their minimums down this way, because normally it would loop down and around and come back up, right? It keeps everything positive, so it just keeps balancing things up. Kind of an interesting pattern. And now the last one is the most interesting because you have a bunch of stuff going on. I broke it down into 4 different functions. I did x and sine x on top. Those are being multiplied. I have x squared plus 2 on the bottom. So I have a linear times a trig function, they're both continuous, divided by a quadratic, which is continuous. And notice also it's never equal to 0 because I shifted it up too. So these are all continuous, and then I put them inside as a composite. I put them all inside of an absolute value function. So it's kind of like I created a function f, which is h of x times j of x divided by k of x, and then I put f of x into g of x. And because all of those are continuous, my new function that I'm calling f of x is continuous. That one's a little bit busy, but as it says, in all 3 examples, g and f are continuous functions, and so by the properties of continuous functions, these are all continuous. And you may need to be using that reasoning just a little bit in some of the problems out of section 2.3, which there is the assignment, and I do the first 24 problems, if you would, and then we will be able to talk about them. Oh no, not again. This is getting embarrassing. Oh yeah, there he is. You jerk. Stay away from my stuff. Oh, he just flew away with like 6 of our problems. All right, well, I guess we'll just do the first 18 tonight then. Good luck. Let me know at 3 o'clock if you have any questions on these, and let me know if you have questions about anything. Hope you're having a decent Tuesday, and we'll talk to you later.